Okay, now let's consider continuous system for tension and compression. Let's see this example. This example is a beam. It's just like cantilever beam, but shape is slightly different. Some tapered cantilever beam we can consider. Of course, the cross section is a circle, and on the left side, the external force P is acting like this one. Of course, the material is homogeneous and uniform. And dimension on the right side, here is diameter dB, and left side dA. When external force P is acting like this one, when this material has characteristics of Young's modulus E, then we would like to calculate delta A, deformation or elongation on the left side by external force P. In order to consider this problem, we can draw a figure like this one. The shaded area is original shape, original form, and right side dB, left side dA, that's the same. From when you extend this line, you can find O point like this one, and from 0 point, O point to some place X position, we can have some small infinitesimal component. It's very thin disk. When I pick up this one is like this one. Thickness is dx, and the diameter is dx, this one. And when I draw free body diagram, external force is loaded like this one and this one. It is in the state of equilibrium. When I say this cross-section area is A1 is 5/4 dx squared. Okay, we can calculate total delta A. Delta A is integrated from here to there, the delta. When you sum all the small infinitesimal one, then finally you can get delta A. d delta, this one, P dx over EA1. P dx EA1 is available. Then we can take integral from this point to that point, LA to LB. Of course, there is a relationship between L equals, this distance equals LB minus LA. Okay. Our goal is to find this one, the elongation or deformation, and how we can properly take this integral. In order to that, we can have some similarity relationship between two triangles. When you consider this small triangle and large triangle, and dx, this distance, this radius over dA is x over LA. Okay, you can draw this way. Next one, LA is given this one, and when I rearrange this one, then you can have this relationship. dx is substituted there, and finally the delta A is integrated d delta, and P dx E 5/4, everything in it, substitute. Then final value is like this one. If you get some integral, then finally you can have some final answer, millimeter. It is expressed in millimeter. Okay. Here we assume some taper here. This angle is very small. When this angle, let's say this theta angle is very large, then we cannot apply this kind of approach because the relationship is totally different. With different perspective, we solve or we approach this problem. Okay, here mainly we applied the relationship between elongation delta equals P L over Young's modulus and cross-sectional area. This kind of formula was applied. And if we did continuous system, we can change instead of delta, d delta and dx. Instead of delta and L, we apply there. Then we can have, then when you accumulate it, when you sum it up, then finally you can get answer like this one. Okay, that's for the continuous systems case example.